Many products claim that they can suppress thermal runaway. Today we're going to put that to the test. We're going to be testing out a fire blanket and the cold fire extinguisher. For this test, we're using 170 18650 cells to simulate a hybrid battery pack. The average EV has over 2,000 individual lithium-ion cells. These cells are enclosed within the vehicle structure, preventing extinguishing agents from directly reaching them. This is the greatest challenge that first responders face. Here we have 170 18650 cells, an oxygen-rich environment, and we've removed all protective casing to expose the individual cells, creating an open cell configuration for testing and analysis. At our labs, we have multiple means of initiating thermal runaway. For this test, we had initially wrapped individual cells with a heating element that gradually heated them. This was taking a long time, so we pivoted and added an external heating element that was burning at 450 degrees Celsius for over 30 seconds, and we directed the heat to specific cells, which initiated thermal runaway quickly. In our first test, we're going to validate this manufacturer's claims that their EV fire blanket can control and suppress thermal runaway. This fire blanket significantly reduces the amount of oxygen that this thermal event is receiving. So while it is temporarily controlling this event, it is not extinguishing this fire. Our second test tests the claims of the cold fire extinguisher and its ability to stop thermal runaway. The cold fire extinguisher claims that it will cut off oxygen to these thermal events and actively cool all of the cells. To ensure the accuracy of our research, we initiated thermal runaway in the center cells that had not previously experienced a thermal event. This ensures a fair test and preventing skewed data. Utilizing a thermal imaging camera, once a cell went into thermal runaway, we encapsulated that cell and the adjacent cells with the cold fire solution. The cold fire extinguisher did an excellent job knocking down the flames. Unfortunately, our thermal imaging camera showed temperatures above 250 degrees Celsius in the actual cells that experienced a thermal event, and notice a rise in temperature into the adjacent cells. We had covered these cells in a lot of this cold fire solution, so we decided to give it some time to allow the solution to do its job and cool the cells. We noticed that the cell temperatures were trending in an upwards direction, so we decided to then put more of the cold fire solution on only the cells that were experiencing a thermal event and the adjacent cells. Utilizing our thermal imaging camera, we noticed a rapid increase in temperature in a handful of cells. To test the cooling properties of this extinguisher, we focused the 70% of solution left in this canister on only those handful of cells that were experiencing a thermal event. After discharging the entire contents of this extinguisher, it did knock down the initial flames, but it did nothing to cool the cells or stop the propagation between all the other batteries within the pack. In our test, we use an open pack design. This gives a significant advantage to the cold fire extinguisher. If the pack was closed, it would act like a convection oven, superheating all the cells within it, allowing for quicker propagation between cells. But in an open pack design, it allows the heat to escape and dissipate into the environment, so cells do not propagate as quickly as they would if it was an enclosed pack.